So welcome back. We are about to kick off the second half of today's lecture. And, well, actually, I don't like to call the word lecture. Today's course session, because this is not a lecture. Your colleagues here are actually helping me a lot, and we're doing a lot of exercises. So there is really no distinction between what we are doing today and the exercise sessions or whatever else. These are sort of learning experiences mostly for me. So before we took a break, we were coming to grips with the clean star operation. Now, very often, in order to understand an operation over some object, like for instance languages, it's a good idea to understand what it does on some pathological cases. Remember, for concatenations, we look at A concatenated with the empty language, and that somehow forces us to use the definition of concatenation to understand precisely what the result should be. If we use the definition, we are in good hands. So let's try to do the same also with the clean star. The clean star can be used for any language. So for instance, it can be used for the empty language. If we take the empty language star, what is it that we get? Okay, one of your colleagues is saying the empty language. And let me call this guess one. Okay? Now, do we have a guess two? Before you guess, and in fact you shouldn't guess, try to think about the mantra. The empty language star consists of all the strings that you can form by taking any number of strings from the empty language and write them one after the other. Any number can be 0 or more. Now think about the empty language also. It can be thought of as an empty alphabet. So in that case, empty set star would be the set of all strings that you can write with no symbols. How many strings are there that you can write with no symbols? There is one string that you can write without any symbol whatsoever. That's the empty string. And in fact, the empty string is what you write by taking 0 strings from the empty set, and that you can do because you don't have to take anything, and write them one after the other. So actually this thing is the set that only contains the empty string. That's what it is. Yeah, the empty set, call it. So what if you concatenate? Well, okay, well, for concatenation, as I was telling you, I was telling to some colleague of yours before during the break, for concatenation, the empty set is like Pac-Man. For those of you who actually played that prehistoric video game, Pac-Man would eat stuff. Well, in a setting of concatenation, the empty set is like Pac-Man. It eats everything else. No matter what you write before it or what you write after it, it will be eaten. And the result will be Pac-Man, the empty language. But this is not concatenation of languages. This is the star operation.
So this is only given by A, as long as A is in the empty set as well. But if you only concatenate the empty set with the empty set, would that also be the empty set?
The question is, what if I took the empty language and concatenated with the empty language? You will still get the empty language. So this A here is just an arbitrary language. It could be the empty language. It could be the language that only contains the empty string. It could be Icelandic. It could be Italian. It could be any language under the sky. But if you concatenate it with the empty language, the result will be the empty language. But if you concatenate something with the empty language star, then everything changes. That's the question. The question is, hey, I got my friend. So let's extend the page. You see, this thing here, and let me put braces here to disambiguate the parsing. This is not the same as this. Why? Because this is an empty language. This is not an empty language. This is the language that only contains the empty string. So this thing actually will be A, and this thing will be the empty language. The two are going to be equal if and only if, in one case, when A is the empty language. Sorry, absolutely, absolutely. Thank you. Fortunately, somebody is awake, and it's not me, unfortunately. Absolutely. Thank you. Saved me from a major embarrassment on YouTube. So this is it wouldn't be the first one. It wouldn't be the last either. So it takes some guts to go live on YouTube and make a fool of yourself. Well, a lot of people actually do, judging from YouTube, but that's another matter. That was not my aim. Thank you very much. I got confused. I mean, left and right for me are very sometimes confusing. I just need to remind myself of what is right and what is left. Splendid. Okay, anyway, when in doubt, you can look at the formal definition here that says that no matter what language you take, if you take that language to the 0th power, you get this. And this actually makes sense because with respect to concatenation, the language that only contains the empty string is like 1 in multiplication. Because it's the unit. Everything concatenated with the language that only contains the empty string will give you the language that you started with. That's what we saw before. And we answer some of these questions. Some others are for you for the exercise session. So you can be happy. Now, why am I bothering you with the definition of these operations? Well, that's because they are at the core of the language of regular expressions. Remember, you're at the Unix prompt. You want to know, for instance, what are all the names of the files in your current directory. How do you do it? You ask ls star. Now, what is star? Star is a regular expression, which describes what? The set of all strings. That's why when you write ls star, you get all the names of the files in your current directory, because they all match the pattern described by the regular expression star. Star is just the cleany star in disguise. That's where star actually comes from. There is no reason otherwise why one should use star. So there are many different formulations of the language for regular expressions. Here's the one that the textbook gives you, and that's the one we use in this course, apart from the automata tutor where you have a slightly friendlier syntax, or less mathematical. It's the same thing. So what are legal regular expressions? How do we define them? Well, it's a language. Languages are all defined recursively. So we give a recursive specification of the language of regular expressions that tell us what are the basic regular expressions, and then they tell us how to construct complex regular expressions from simpler ones that you've already built or bought in your regular expression store. Okay, so what are the regular expressions over some input alphabet I? Well, the empty set is a regular expression. Intuitively, it describes a pattern which is matched by no string whatsoever. It describes the empty set of strings. All of those that match the pattern empty set. There are none. So it's a pattern with no match. Lambda is a regular expression. Well, this describes the set that only contains the empty string. It's a pattern that is only matched by the empty string. Okay, so remember, this is a language for describing patterns. Patterns may or may not be matched by some string.
Is there any difference in the output? You list the star, there's nothing in there. You get the same output.
Okay, so the question is there any difference in the output? So if you're in your current directory, there is no file, so there is the empty, so the language of all the file names in your current directory is the empty language, then you get no match. And this is natural because, okay, even though you're asking for, give me all the names of the files in your current directory, if there is none, it cannot return anything. So nothing matches. But that's a very special case. It's it's the only instance where give me all the file names will return no output, because there is nothing. But if there is only a single thing in there, then you will get it. Okay, so for every symbol in your input alphabet, you have a regular expression, which is just that symbol. We just write them with capital letters because Rosen does so, and also to distinguish regular expressions from the patterns that they describe. So this describes a pattern that is only matched by one string, namely A. So if you are at your current directory and you say LSA, well, either you get your file name, assuming that you actually name your files A. If there is a file named A, you will get A back. Otherwise, you get nothing. Okay, so far so good. These are all the basic ingredients. Now the fun starts. Well, actually, the useful part starts. How can we build complex regular expressions from these components? Okay, suppose somebody gives you two regular expressions, A and B. Then you can build the regular expression A followed by B, very often written without the dot here. So what does this describe? This describes the concatenation of the language described by A and the language described by B. So this is the collection of all the strings that you can split into two parts. The first part matches the pattern described by A, and the second part matches the pattern described by B. So if you ask at the Linux prompt, give me all the file names, ls, ab. Well, that's a complex pattern. It's A followed by B. Well, either you get AB or you get nothing. And why? Because, well, that's what you ask for. Union. Union is like OR. This describes all of the strings that either match the pattern described by A or the pattern described by B, possibly both. It's like in the union. It's the union of the language consisting of all the strings that match the pattern A and the language of all the strings that match the pattern B. One or the other, possibly both of them. Give me all of the strings that either have a name that starts with an A, so have a name that starts with an A, or have a name that starts with a B. That's how you do it, with a union. And our good friend, the cleany star. If you have a regular expression A, then A star is a regular expression, which is matched by what strings? Well, the empty string is always matching that pattern. If the string is non-empty, it matches A star. If you can chop it up into a sequence of strings, each one of them matching the pattern described by A. Example. Okay, so let's consider this simple pattern here. AB star. This actually is going to describe exactly the language that we had before in one of our examples, namely the set of all strings that you can write down by concatenating any arbitrary number, finite number, of the string, copies of the string AB. Okay? Why? Let's take, for instance, this string here. Why does it match this pattern that we describe here? Well, what was the mantra? The mantra was this string here matches the pattern described by this regular expression if and only if we can find a way of breaking up this string into substrings, each one of the substring matching the pattern AB. In other words, each one of the substrings being AB. Okay? I split it in the obvious way. 3 parts of ABs. Okay, so this string matches the pattern AB star, because we can split it as 3 copies of AB, and AB is exactly the pattern I'm taking the star of. Let me give you another example, or let me ask you to work on a different example. Suppose that I take this pattern here. Star. And I take the string does this string match the pattern A, B, union A, all star? Somebody said no. More people said yes. So let's convince whoever said no that the answer should be yes. Okay, so what does it take for this string to match this pattern? We have to split it up into substrings that concatenate together, give us this string that we have here, AB, AB. And each one of the component substrings in our split should match the pattern AB or A. That is to say, it's either AB or it's A. Okay, there are many possible splits of this string, but some of them are obviously not right. For instance, would it make sense to take the first A as one of the components in the split? Okay, well, the single A here would match this. But then what follows start with a B. And then we are in trouble, Houston, because all of the 2 possible patterns that we want to match start with an A. So that's not a good idea. So let's split it here. Now, with AB, we are fine because we match the first pattern. Where do we split next? We take the A alone. This matches the A over there. So let's say this matches this. This matches that. And now we are left with an AB, which we could, of course, try to split, but we don't. Why? Because AB matches the pattern, the red pattern. Bingo.
So when you split it up, do the strings have to start with A, B, or A, or is it enough that they include A and B?
Okay, so the question is, when you split it up, is it enough that the strings start with A or AB, or do they have to be A or AB? Well, include A and B. Well, you know, the order matters. So if they include A and B's arbitrarily, then no. So this is not going to be right. So for instance, if you look at this pattern, ABA, then you can argue that this pattern actually matches the regular expression AB union A star. So that's okay, provided that what follows matches the regular expression A union A star as well. Splitting after the first A will not work, because then you would have to match what follows with the regular expression AB union A star, and what the string that you're trying to match starts with a B, and nothing that you can build using that matches this regular expression that we have starts with a B. Yeah.
Is there then some way to make wildcard or something?
Okay, is there some way that that's a good question. That's a good question. Let's look at the language that we had before. In this language, actually, there is no star. So in the regular expressions that you use every day, you can write star, just the symbol star, like ls star. Star is a description of a wildcard pattern that is matched by anything. But it's not here. Here, the only use that we can make of star is give me a pattern, take the star of that pattern in the form of a Kleene star. So aren't we missing this wildcard character? Well, of course we are not, because otherwise there would be a mismatch between what we see here and what is actually practiced. So the wildcard pattern is actually something that you can express, provided you know what are the symbols that you use to write strings. So for instance, if let's say sigma is the collection of the ASCII characters, which are typically what we use in computer science, at least, then what is the star in Unix? The star in Unix is nothing but sigma star. And sigma star is first character in ASCII, or second character in ASCII, or 256th character in ASCII, or whatever they are. I never remember how many they are. Star. So now you can appreciate why Linux gives you the wildcard star as a shorthand for this. It's pretty useful, but it's a shorthand for a bigger regular expression that we can write in the syntax that I gave you before. Give me the alphabet that you want to use. Say ABC. Then star is nothing but either A or B or C star. If you want to use the English alphabet, either A or B or C or blah, 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 Z star. If you want to use the binary alphabet, then it's a short sort of 0 or 1 star. But the thing is, the wildcard is there. It's just syntactic sugar, as computer scientists love it to say. If you haven't heard this expression before, you will many times. Yes.
It doesn't matter if we change the order, AB is in front of the union or A.
I'm writing on the slides. Sorry. So in this parenthesis here? Oh, okay. So the question is, does it matter whether you write AB union A star or A union AB star? It doesn't. It doesn't because union or is commutative. Good question. Another good question. Is there an exclusive or? Well, not explicitly in the language that I gave you before. But it's an interesting question to ask, can we actually express it? For instance, another pattern that is not there is, I want a pattern that is satisfied by all of the strings that do not have AB in them. It's a negative pattern. We don't have it. Can we express it? Are we losing something? The answer is no, we have them all, but it may require some coding to express them in some way. Excellent questions. Keep them coming, even though they are a little bit more advanced. So you can see I turned this thing into Mickey Mouse. I keep doing that because I'm still, what the bloody hell? Yeah, I love them. Okay. This thing is still there. What have I done? It's alive. I'm not, unfortunately. So it's okay. So can I erase those things? Let me try, because otherwise it's gets. Yeah. You can see this is what you get when you go live on YouTube. Fantastic. Okay, so now I have to be careful here. PDF. Oh, whew. Okay, so we have basically already described informally. Yes, there is a question. Okay, why is not B star a regular expression? You know, these are arbitrary A and B, so B star is also a regular expression. So you can just swap the roles of A's and B there and you get B star. So in other words, take any regular expression under the sky, B star, that regular expression star is a regular expression. So this is just to save one line. I should have put it actually on a separate line. Anyway. Okay, so basically, given any regular expression, you can describe the language of all strings that match that regular expression. I've given you the informal definition. This can be defined formally, recursively. And that's an exercise for you, or you just look at Rosen's book. But what I've said informally suffices for all the uses that we want to make today. So let's see actually whether this suffices. Let me give you some examples. Okay, the first one we have already seen actually, because I've already told you what that is. How many strings match this pattern? Only one, namely the empty string. Excellent. Okay, so if you were to describe to me in English what collection of bit strings, what bit strings actually match this pattern here, what would it be? Okay, so it's an infinite language, so don't give me all the strings in it. We will never finish. Just give me the property. Okay, 0 followed by 0 or 1 in any order, which means all the strings that start with 0. Afterwards, I don't care, because 0, 1, 0 union, 0 or 1, as many times as you want, is just a collection of all bit strings. Okay, let's look at question number 3. That's a De La Soul thing. Can you give the answer? 0 star followed by 0 star. What is this thing describing? Perhaps in a roundabout way. 0 star, namely the set of all strings that only contains zeros. Possibly none, so possibly the empty string. Why? Remember, this is a concatenation of two regular expressions, which happen to be the same, 0 star, 0 star. When does a string match the pattern 0 star followed by 0 star? If you can split it in two, the first part of which satisfies the pattern 0 star, that is to say, it's a string of zeros. The second part of which also matches the pattern 0 star, that is to say, it's a string of zeros. So if you write a string of zeros followed by a string of zeros, what pattern are you matching? 0 star, namely a string of zeros. So this is another way of writing 0 star. It's a longer way of writing 0 star. Absolutely, possibly none. You write no zeros, followed by no zeros, you get no zeros, the empty string. Absolutely. The empty string is equal to the empty string concatenated with the empty string. So actually, you can split the empty string into two parts, which are both empty. And the first empty string will satisfy the pattern 0 star. The other one will match the other pattern 0 star. In other words, you can write the empty string by writing nothing and then writing nothing again, and then possibly recursively thereafter. Okay, so now look at question number 4. This is slightly trickier. What is the collection of strings which is being described by this regular expression? Now you got a star inside a star. Okay, somebody said, okay, so let's, I think we need the scratch pad. Let's see if I can make a mess of that too. Let me make it slightly smaller so we can have also access, at least while I write, to what we had before. Okay, so that's the thing that we want, okay? 1 star, 0 star. And we are wondering, what are the strings that match this pattern? Okay, so there is this star on the outside, but let's look at what's in the inside of the star. What is inside the star is the pattern 1 star followed by 0. The overall expression will be matched by any string that we can write by concatenating substrings that match the pattern 1 star 0 as many times as we want. So what is the form of strings that match the pattern 1 star 0? Okay, any amount of ones followed by 1 0, because 1 star says write some amount of ones, possibly none, but then you have to write a 0 afterwards. Okay, so we do this once, so we write some number of ones followed by 0. But we can do it again. We write some number of ones because we have a star here, no? Followed by a 0. Then some number of ones followed by a 0. Suppose I stop here. And remember, this number of ones could also be 0. And in fact, I don't just need to stop after 3 repetitions of this pattern. I can do it as many times as I want. Okay, so first of all, if I repeat this pattern 0 times, I get the empty string. So the empty string is always there. But if the string is non-empty, we are nearly there. I'm not quite non-empty. I scared her. I wonder why. Sorry for the people who are not with us. You don't understand this bit. But anyway, it's not important. What matters is this pattern here. Okay, so what did you say before? Somebody said something, which I have forgotten. So what is this pattern? Okay, start with ones. But do you think we have to start with ones? No, because actually n1 could be 0. I write 0 once, and then I write a 0. So I don't have to start with 1. Not necessarily. Any amount of ones followed by zeros. Then any amount of ones followed by 0. So let me give you a couple of concrete things. Can I write the string 0, 1, 0? Does it match the pattern? It does. I write 0 once, then I write the 0. I write 1, 1, and then I write a 0. That's okay. Okay, how about this? 0, 0, 0, 0, 0, 0, 1, 0. Yes, that matches the pattern. I write 0 once, then a 0, 0 once, then a 0, 0 once, then a 0, until I write a 1 and then a 0. How about this one? 0, 1. It doesn't match. Why not? Because you have to have a 0 at the end. Could it be what this thing actually says? All the strings that are either empty or have a 0 at the end. Because actually, could it be? Think about it. Convince yourselves whether this works or not. Because I think we're about to be kicked out now. Oh, the question is, can we have 2 ones in a row? Yes, you can, because you have a 1-star pattern here that can be matched by any number of ones. So you can have 2 ones in a row. In fact, you can have any number of ones in a row you like, possibly not. Okay, so if there are no questions, we just adjourn to our Thursday meeting. Thank you very much.